to preserve that. And that's it. So I don't know if I have any time left for questions. Do you have a couple of minutes left for questions? If anybody has any, be happy to try to answer them. No questions? All right. Well, thanks for having me here today. If you have any questions you want to ask later on after I'm back in the room, just come grab me. Thank you.
Thank you so much, Dr. Votler. Really appreciate it. Moving forward in our program this afternoon, the next agenda item for discussion, we actually have two speakers on it. Tina Hansen is a senior project manager on Garver's Texas water team with 32 years of experience in the water industry. Tina's civil and environmental engineering and construction management experience includes water and wastewater treatment permitting, process evaluation, plant design, plant operation and maintenance, and much more. Kyle Kruger is a project manager on the Panhandle GCD water team with 11 years of water and wastewater design and construction management experience. His water and wastewater project experience includes evaluation of system hydraulics and implementation of pumping and advanced treatment processes. Kyle is leading multiple projects dealing with water reuse for potable applications. Kyle has successfully led multiple water and wastewater projects ranging from $5 million to $50 million. Please help me welcome Tina and Kyle.
Thank you. Just wanted to reiterate Todd's comment that it's great to be here this afternoon. This is a great workshop and symposium. And today we're going to move forward with looking at a case study of water supply investigations. There we go. So we're going to go through a couple of steps through this presentation. One is looking at project background and project drivers, looking at alternative water supply evaluations, the steps that go into that process, the summary and comparison of alternatives for this project, and then the steps forward to development of new supplies. So just a little bit of background on Lawton. So Lawton's current water supply portfolio is comprised solely of surface water. So they have 3 reservoirs. They all have about the same amount of yield in a normal year, but in drought, that yield is severely diminished. And you can see during 2015, Lawton experienced one of the hardest hit areas in Oklahoma during the last drought. Similar to the Panhandle, you can see that that drought was pretty significant. The usable storage in Lawton's 3 water supply reservoirs dropped to 41% in 2015. So the conservation pool level in Lake Waurika dropped 20 feet. You can see there on the left in 2010, and that reduced surface area and volume in 2014. So that drought was pretty significant. At 41%, Lawton was on the verge of in their conservation plan of going to mandatory no outdoor use of water at all, similar to what Wichita Falls had experienced. They were on the verge at 40%. They were going to ban all outdoor water use. They didn't quite get there, thankfully, but they were on the verge of that. So supply train motivated Lawton to add 5 to 10 MGD for additional water resources. So as Benjamin Franklin points out, when the well is dry, we know the value of water. When water is plentiful, people seem to take water for granted. So the goal for Lawton was to diversify the water supply portfolio through addition and utilization of a drought-resistant supplies.
Thanks, Tina. I'm going to kind of walk you guys through the alternatives that we looked at for additional supply. Starting off, the additional supplies needed to meet not only the end-use requirements, which would include the quantity of water and the quality of the water, but also they have to address concerns with public perception. And that's really kind of lumped up into a few different factors: the social factors, economic factors, and environmental factors, all associated with that new supply. As you'll see in some of these, some of those factors have a heavier weight depending on what the supply source is. And that, based on the title of this topic, you'll see that diversified portfolio really helps to promote a long-term stability for the water supply, even in those challenging conditions. And in these particular conditions, we're talking in drought. Tina showed you those reservoirs, and they showed the 60 MGD of yield, which is more than ample supply under normal conditions. But that 2011 to 2015 drought period really put a strain on those surface water supplies. And without another source of water, they were going to continue to see issues until the rains came. So going through this graph here, we identified with the city they wanted to see 5 to 10 MGD of additional water coming from a new source. Their average conditions, they use about 20 MGD, so that would give them up to 50% of additional supply coming from another source in those critical times. And the supplies that we looked at included non-potable supplies, direct potable reuse, indirect potable reuse, and groundwater. We've got a kind of a mixed crowd here. I just want to kind of clarify on reuse here. What we're looking at is taking water from the wastewater plant, treating it further, and bringing it back to the drinking water supply. And indirect potable reuse, you actually treat it, send it back to the supply reservoir, whereas direct reuse, you take it directly from the wastewater plant to the water plant, again with that additional level of treatment. Starting with the non-potable applications, really, this is probably one of the more effective approaches if it's implementable. It's right up there with conservation. Basically, they can trim demand and save on treatment costs. If you can find non-potable applications, you're not treating the water to the same level as drinking water supply, so it's going to save on those costs. Some of the applications for non-pot, and this could come from a groundwater source or wastewater treated to end-use requirement. Irrigation is a big one, especially in the summer months. You'll see, they talked about here in Amarillo, doubling their amount of water usage in the summer months, and that's largely attributed to irrigation. Industrial and commercial users account for a lot of water usage. If you have a industrial area, a lot of times they use a lot of water, and they use it in processes, whether it's heating and cooling towers or making paper or a variety of industries. Some of that water doesn't need to be treating to drinking water standards. And then institutional and municipal applications, a lot of time you're looking at ball fields, again, with irrigation, but sometimes there's other applications that those facilities will have that may not require the same level of treatment as drinking water. Unfortunately, the limited demands for non-potable applications in Lawton and the requirements by the end users for the water in non-potable applications limited the opportunities. And I want to emphasize that's beyond what the city already had in place. This map is kind of a highlight of the high-end users in the city of Lawton. We were able to look at data and identify the high-end users. And outside of these users, 2 of them are already utilizing non-potable applications fairly extensively. On the right side, you'll see the Comanche Power Station. They have an agreement with the city to take up to 5 MGD from their wastewater plant to use for cooling water at the power station. So that's quite a bit of water right there. And then in the central part of the city, there is Cameron University. They have developed a groundwater well. They don't treat any of that groundwater. It's a brackish groundwater, but they're able to use that for irrigation of their common grounds at the university and reduce the demand of water they need from the city of Lawton's drinking water supply. So again, the non-potable supplies, it's a great option, but just unfortunately for Lawton, they had already kind of tapped into what was available. Direct potable reuse, touched on, that goes directly from the wastewater plant after additional treatment to the water treatment plant. There is an engineered storage usually in between those processes to allow that water to make sure it's to spec, and even with the direct potable treatment, you're blending that with your treated water supply. So typically you're not going to see more than at a max of 50% of your water from reuse water blending with your treated surface water. And one of the reasons DPR was such a positive thinking by the city and feasible is because their southeast water treatment plant is within less than 3.5 miles to their wastewater plant. So that proximity really cuts down on some of those costs associated with conveying water from one facility to the other. But DPR has some challenges by itself, regardless of the proximity. Public perception is a major one. That ick factor, people saying, I don't want to drink my wastewater. The technology's there and the requirements are in place to protect the end users with reuse waters. CECs and pharmaceuticals are also something that are coming up. Again, there's treatment out there, but as people are able to test to lower limits and find new hormones and pharmaceuticals out there, they raise concerns on, is that in my drinking water? And you'll find a lot of these pharmaceuticals and personal care products that they're finding and raising concerns about. They're already present in drinking water supplies, but the levels most of these are showing up at are very low and do not pose a significant health risk. Total dissolved solids is a major component for DPR. And this is generally, if you think of brackish waters, kind of think of, to simplify it, salt water has a lot of TDS, that salt in there. It's not a health risk, but it is an aesthetic thing. People aren't going to drink water if it tastes salty, so you have to address that. And unfortunately, for inland facilities, treatment of TDS is fairly expensive. It requires high-pressure membranes that actually provide a physical barrier to remove those constituents. And then you have to come back and do something with that brine, that concentrate that's actually filtered out. You have to have a disposal method for that, and that generally drives up the cost for that level of treatment. Regulatory hurdles are also a challenge. Oklahoma is actually just gone through the process of developing regulations for reuse on the indirect side. They have passed that in their regulatory agencies and have sent that to legislation. So fingers crossed this year they will have a regulation in place for implementation of IPR, where here in Texas they have a lot of IPR facilities, but they do it on a case-by-case scenario with TCEQ. This law in Oklahoma will have a standard path forward. And then you've got multiple treatment barriers. IPR, you're taking the water back to that supply reservoir, and there's that natural environmental buffer there. With DPR going from the wastewater facility to the water facility, they require additional treatment barriers. Again, kind of a fail-safe. If one goes wrong, you're still treating to a level that protects human health. And the last thing is, if you treat your wastewater to a higher level and remove more constituents, you're going to have to address the additional solids that come into play, and that can increase the cost for treating the wastewater, so it's something to be mindful of. And on the DPR side, disinfection is pretty stringent. These values shown on the graph here, the 10, 10, 12 log removal, just to kind of give you guys some context. I don't know how many everybody here is familiar with log removal, but a 1 log removal represents a 90% reduction in the concentration. And you increase that tenfold each time. So you're talking 99.99999% removal when you get to 10 and 12 log removal. You're really removing most of those constituents. And the unique thing here is that, we talked about reverse osmosis and high pressure membranes being required for that TDS and the aesthetic factor, but those membranes also can be required for these disinfection requirements, but we've identified treatment without the reverse osmosis to get to these levels. And that's through advanced oxidation, creating a hydroxyl radical to get that vector destruction of Cryptosporidium, Giardia, and virus. These are kind of benchmark organisms used to make sure the water's treated to a safe level. And just for context, IPR has 355 limits on their level of removal, so you're seeing a much higher, again, level to account for that reduced level of barriers. On the IPR side of the project, we evaluated that. Tina mentioned they have 3 reservoirs, and we looked at conveying treated reuse water to 2 of those reservoirs. And the reservoirs actually, they give you that environmental barrier, which is very nice to kind of eases some of that public perception. And actually, to the level of treatment on the water can actually improve the water quality of these reservoirs. So in reservoirs, you often see issues with impairment for growth of algae or sediment, turbidity issues, and that impacts the aquatic life in these reservoirs. With augmentation of a reuse supply treated to the required levels there, you can actually see the impaired body have lower levels of nutrients and solids based on that added augmented water. But IPR does have challenges. That enhanced nutrient removal requires more treatment at the wastewater plant, and you're talking about a new treatment, not necessarily for human health, but for the aquatic life in the reservoir where the receiving body of that water. So, we'll see nitrogen removal required typically, but to control algae growth, phosphorus has to be removed to a much lower level, and that requires additional treatment and expense. Again, that increases the solids production at the wastewater facility, and they have to be able to handle those additional solids. Increased infrastructure costs and additional conveyance. Just to give you a frame of reference, both of these reservoirs are close to the same distance from the wastewater facility. One of them you could gravity feed a good ways down to the reservoir, but it is a shared reservoir. The one on the right, that's Waurika Lake, and its water quality is a little bit less. So after evaluations, we identified the Lake Ellsworth Reservoir to be more favorable. And you look at the conveyance, you've got to identify the size of the line for efficiency of pumping and full build-out of facilities. If you want 5 MGD now, but maybe 10 MGD in the future, you have to size that line to make sure it can pump that water efficiently. And you're seeing that reservoir provides drinking water, and you're paying money to send water through that conveyance line, and it's got to be a dedicated conveyance line separate from the one already in place. And the public perception. Even though the water is going back in the reservoir and it's a cleaner water, you still have to overcome that factor and spend some time with the public to educate them on the value of that water, especially for the beneficial uses of those water bodies. I want to touch a little bit on another portion of evaluation we did that's can be lumped in with IPR, and it's called riverbank filtration. In this scenario, we take the wastewater and let it discharge into its normal stream. Then downstream from the wastewater plant, if the alluvium is suitable and the geology is suitable, you can actually install pumps into the alluvium. So you're talking shallow groundwater pumps, and you get this filtering process from the riverbank filtration to pump that water back to your water plant for treatment. And we did this evaluation sequentially. We looked at basically a desktop level. And so before the city spent a lot of money to actually go out in the field and do test pumping and all that, the desktop analysis showed that the permeability of the layers of material around the receiving stream were not favorable for this process, so we did not evaluate it any further. The last alternative supply we looked at was a groundwater supply. A lot of cities have groundwater supplies. Lawton had not used the groundwater supply, and the aquifer in Lawton is the Arbuckle Timbered Hills. There's very limited data about the Arbuckle Timbered Hills. It was known that it is a brackish water. Constituents of concern that were known included fluoride and TDS and levels that would require treatment. So the limited data supported this phased approach for evaluating groundwater. Rather than just go start drilling wells and seeing how much water we can pump out of the ground, we kind of took a phased approach. We started off with the desktop analysis to look at the well logs that were available and see what the data showed from there. And from that, you'll see on the map the square boxes. Those looked at the desktop data available as well as faults within the aquifer to identify favorable areas. Then we came back and looked at geophysical investigation. And this is really a neat process. I don't know how many of you guys are familiar with water witching, but it's a little bit more scientific than water witching. They measure resistivity in the ground by setting up instruments in the area and looking in the ground and measuring that resistivity, and that gives them some data on what they'll expect to find below the surface without having to dig into the ground. One of the unique things that we did with that geophysical investigation, we started off with those desktop quarter sections and then went back with the city and identified city-owned properties. All that orange is city-owned properties, and we developed additional sites to do those geophysical investigations, and then based on those kind of rank sites for drilling test holes. And test hole drilling it does have a cost, but it's more cost effective than trying to drill a production well in an area that you're not certain. It's probably about 10% of the cost of a production well. And this allows you to, during a test hole, they will drill down into the extents of the aquifer. They will pull water samples and corings and cuttings. You'll get a profile of the geology of the aquifer. They'll do a drawdown on the aquifer to tell you what the estimated yield is. It's an estimated yield at this point because it's not the full-size bore, again, trying to preserve your money. And they take samples of water while they're doing that pumping and send it off for water quality analysis so that you know what constituents are in that groundwater. And the test holes that we had were drilled at key locations, and they showed that there was sufficient supply within the Arbuckle Timbered Hills Aquifer to supply Lawton. We drilled a total of 10 sites, and 5 of those were identified as favorable. A couple of those ran into crude oil, but these 5 here show that they were able to get an estimated yield of almost a little over 7 million gallons per day from those 5 wells. And then the other important factor, we touched on quantity and now quality. Looking at this table here, you'll see the constituents of concern. Really, arsenic is something that wasn't anticipated that was found at the majority of sites. Chloride was negligible at most sites, but there was one elevated. And fluoride, I mentioned on this, and this is a big one. Outside of Site 1, everything was at 8 milligrams per liter or so, and that is 8 times the primary level or secondary level of recommended. And iron is another one that is on those. All the ones in orange represent secondary standards, and secondary standards with the drinking water represent those that are related to aesthetics, whether it's taste and odor. But typically, if you're going to add a new water supply, it needs to meet or exceed the existing water supply quality, so those were important to know. And then that last one, TDS, is always going to be something that you have to look at with brackish supplies. And typically, as you get down deeper into aquifers, you'll see TDS go up, and that secondary limit is 500, and the surface water supply the city has around 300. So if you increase that, then you're going to get complaints again about that salty taste of the water. And so based on the results from the quantity and quality, we looked at the end level of treatment requirements. The graph shows kind of, you start off with your groundwater supply, and is it going to be used for non-potable or potable applications? We already kind of ruled out the non-pot. Then the potable, can you do full treatment or can you blend? So we've got high TDS in the groundwater, but that surface water has lower TDS. So if we can blend partially treated groundwater with the surface water and get an end result, then that can save on the treatment cost of the groundwater. And then you look at centralized treatment of the well sites versus individual wellhead treatment. And again, that depends on the amount of treatment required. Looking at those constituents that did come up, we identified multiple technologies would be required to address the constituents. This table shows that each of these processes listed here has more effective approach for different constituents. So what we came up with is a combination of high pressure membranes and oxidation and filtration process for treating that groundwater. Oxidation and filtration will knock out the arsenic and lower the level of fluoride. And then the high pressure membranes can be used for polishing to take that TDS out and an additional fluoride as needed. And so that really kind of set the stage for moving forward with a groundwater supply. Kind of want to summarize the comparison of IPR, DPR groundwater supplies. Going through the list here, treatment requirements, they all have their own challenges. IPR having the higher levels of nutrient removal adding for treatment costs. You would have to update your TMDL for your reservoir that receives the water. And the regulations at this point were pending, but again, I mentioned those are moving forward. DPR, you've got less barriers, so you've got higher level of treatment, and that drives up the cost. You've got, at this point, Oklahoma does not have DPR regulations, so that would be a hurdle to overcome. And then with the groundwater, you've got higher TDS in it than you would the reuse supplies, and you've got other contaminants, the fluoride, the arsenic, and the iron that would have to be addressed. But you do have the option there with blending to help reduce the costs associated with that. And then you look at the groundwater wells and conveyance infrastructure associated with implementing your new supply with the existing infrastructure. IPR, you've got a large diameter, long distance pipeline. I believe it was 23 miles to get back to the closest reservoir. And I believe we're looking at least a 24-inch line. DPR had a very short line. We touched on that, 3¼ miles from the wastewater plant to the water plant, so that's a plus. Groundwater, you have to convey from the well sites to the central facility or treat at the well sites and fully treat it and integrate with the system. Ideally, you'll find groundwater wells in close proximity to where your centralized treatment is to cut down on those conveyance costs. Efficiency. So IPR and DPR, really IPR, you're spending all this money to treat water and bring reuse in and then fill your reservoir, but the reservoir is still subject to evaporation. So in times of drought, you are improving the ability to provide water, but you're still losing a lot of efficiency with the evaporation that occurs in the reservoir. You've got the higher operational costs with DPR, again with those higher treatment levels, the disinfection log removal requirements. And then groundwater has high head pumping and blending options, and of the three, it's going to be the more efficient of the three. Public acceptance, IPR is aided by a natural barrier in the reservoir, but there are those that will be upset about the reservoir and impacts to it from adding treated wastewater to it. DPR requires much more outreach. Wichita Falls and Big Spring, Texas both went through that process during the drought period, and it's a hurdle that has to be considered. It can't be taken lightly. And then groundwater is most readily accepted when it comes to public acceptance. And then for operational flexibility, with IPR, you've got full flow treatment. DPR has enhanced monitoring and intermittent operation. So you have to have constant monitoring of your DPR water since there's not that barrier in place to make sure that the water's safe. And if there's any off-spec water, there has to be a means of recycling it back to the wastewater plant or discarding it before integration into the drinking water supply. And then groundwater gives them the opportunity to phase the growth, and depending on the treatment facilities, there may be an opportunity to use those intermittently, and so that you're not driving up operational cost. And you'll see on the next slide here, I'll show you kind of where the cost came out on that. And then available quantity actually became a concern because I mentioned the wastewater facility provides up to 5 MGD of wastewater to the power supply for their station where they use it for cooling water. Well, the average flow to the wastewater facility is 10 MGD. So in the event that the city wants 10 MGD, there's only 5 MGD available from the wastewater facility currently. So that was a restriction for both IPR and DPR. And then groundwater, we identified in those 5 sites that the yield seemed to be there. It seemed that the aquifer had plenty of available water. There's not a whole lot of permits there and plenty of water rights available. It's just a little bit of a brackish water, so the quantity was there though. And the real takeaway, you look at the cost per 1,000 gallons for these alternatives. IPR actually cost more than DPR, largely due to the extra conveyance. When you talk about 23 miles of pipeline and pumping versus 3.5 miles, that can overcome the additional treatment cost at the local facilities for that DPR. So you see a couple dollars, almost $2 more for IPR. And then groundwater came in the lowest at $2.50. To give you guys a frame of reference, average water treatment cost per 1,000 gallons in the U.S. is $1.50. So any of these alternatives, you're looking at spending more money, but again, you're looking to diversify your supply so that you have the ability to maintain the ability to provide water during drought conditions. And with that, I'll turn it back over to Tina to talk about how we were going to develop that new supply.
Thanks, Kyle. So it's a great summary of the process that we go through to evaluate cost-effective options for new water supply. So what are the next steps to develop that supply once we've identified the most cost-effective option? One is looking at logistically where treatment can take place. So there's centralized treatment near the existing water plant where we can actually treat and integrate the groundwater treatment into that same complex. So it's a good proximity to the production wells that are on the east side of the town, which is where the water plant is as well. There's available footprint at the site. You can see that white roof building is you can see in the plan view the size, and then in that picture, that's the building that the groundwater treatment units would be placed in. Another good advantage for this option is that if you're treating at the same location as your surface water supply, you can blend there at the plant site both your groundwater and surface water, so that you have a well-blended supply, that the quality is uniform throughout the produced water. There's also resources available with existing treatment plant staff and power supply, and then there's reduced disposal costs because of the proximity to the wastewater plant. So any of the brine coming off the membranes can then go to the wastewater plant for processing. The new groundwater supply will be implemented in stages to promote smart spending. So we want to get a little bit more information in stage 1 to really refine the location of the wells and look at the treatability of that groundwater before we move to stage 2, which is actually design and implementing and building the treatment units and the piping required for that new supply. So stage 1 will secure the location of production wells and confirm treatment requirements. So in this stage, we're going to do a few more test holes on the east side of town to further refine location of those groundwater production wells, do some additional geophysical investigations that Kyle talked about, and then the drilling. We'll also do bench scale treatability studies of that groundwater supply to further refine the treatment requirements for the water coming out of those production wells. Then stage 2 includes the detailed design and implementation. So you can see in the graph on the aerial on the right, potential locations for 4 new wells, and then the blue location is one of the existing test holes. So we would do the production well design and implementation, do some more pilot testing to further refine the treatment requirements, and then design the treatment facilities, and then advertise for contractors to build the facility, go through construction, and then commissioning, startup, and training the plant staff on the new treatment processes. So with that, are there any questions? Yes, sir. So the question was, would we have above ground reservoirs to store the treated water? And would it be covered to keep algae from growing? Yes. So typically for a treatment facility, you have a treated water reservoir that you store your water in before you pump it into your system. Those are always covered to be protective of that treated water, to prevent any contamination from getting into that treated water supply. It's also disinfected so that you carry a residual disinfection so it's covered so there's no light getting in for algae, and then also that disinfection keeps algae from growing in that treated produced water that's going into your distribution system for use.
You can also build a storage tank, again, to eliminate that sunlight from growing stuff, but you're pulling a lot of the nutrients out of the water. And if you have a terminal storage reservoir that is exposed to sunlight, you can add copper sulfate or some other kind of biocide to control that algae growth. Right.
Correct, yeah. Yeah, so sometimes you have a reservoir at the front end of your plant that's the raw, untreated water, and I think that's what Kyle was referring to, that you can add some copper sulfate to keep algae from growing in that raw, untreated water storage reservoir. And then on the treated, finished water side, that's usually a above ground storage tank with a roof, and it's covered, disinfected as well.